Alrighty. Well, I'll begin with a word of prayer once I get up here. Dearly Father, we thank you for this day again. I thank you for this class, and I just ask you bless our work today. Help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. So, guys, questions about the homework? Or yeah. 246. Well, oh, duh. So what's your question about this one here? So like we have f of x equals the absolute value of x minus 2. And it says, show that there's no c such that the f of 3 minus f of 0 is f prime of c times 3 minus 0. It says your question on how to do that, or? So this formula, this function is literally minus x minus 2 or x minus 2 in two different cases, right? So this would be for x less than 2. And this would be for x greater than 2, right? And so this is literally the absolute value function shifted over 2. So it looks like something like this, right? It's just a v, right? So what's the derivative of this function? And the function has, equality. Like it is 0 at 2, right? But the derivative doesn't exist at 2 because the graph has a corner in it, right? So like the left derivative, you want to be minus 1. The right derivative is plus 1. They're not equal, so it doesn't exist at 2, right? So you've either got minus 1 over here, you got 1 over here. In other words, the domain of the derivative excludes 2, whereas the domain of the function includes it, right? So for this function, the only values that you're allowed for the derivative are minus 1 and 1. So what is, you're supposed to look at f of 3 minus f of 0, and the question is, can you make that equal to f prime of c times what? 3 minus 0, right? That would be, if the mean value theorem was true, the claim of the mean value theorem was true, then there would be such a c, right? But what is f of 3 and what is f of 0? F of 3 is a 1, right? F of 0 is, absolute value of minus 2. So we've got minus 1 is equal to f prime of c times 3, right? So we would have to find a c such that f prime of c, we'd need to find f prime of c equals to minus 1/3 to satisfy the claim of the mean value theorem. Can we do that? Can we make f prime of c equals to minus 1/3 for this function? We can't, right? Because it's either equal to 1 or minus 1, neither of which is minus 1/3. So there does not exist such a c. Why is that okay? Why does this not contradict the mean value theorem? Yeah. It doesn't fulfill the preconditions, right? The hypothesis of the mean value theorem. Where does it fail? It fails because right here, right, you have f prime of 2 does not exist. So therefore, the mean value theorem doesn't apply. Does that make sense? So, yeah. As a general rule of thumb, if you try to apply theorems where you haven't met the conditions for the theorem, it doesn't have to go well. It doesn't have to fail either. Like there might be a function which is not everywhere differentiable, and yet through a quirk of coincidence, it still allows it. So when you asked this question, I was a little bit worried. Like, is my problem set up wrong? Did you actually find a C that made it work by accident? But okay, good. Other questions? Yeah. 257? Sure. Problem 257. Let's see here. We've got f of x is the exponential of 9 plus 6x minus x squared. All right? And we're supposed to find critical numbers, determine intervals of increase, decrease, as well as intervals of concavity, sketch any local extrema, blah, 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 blah. All right. So let's get to it. First order of business, I'd just like to point out what this is. This is really like e to the minus x minus 3 squared. See, because x minus 3 squared is x squared minus 6x plus 9. So if you factor a minus out of this, wait a minute, maybe I'm wrong. Nope. It's not that. I wanted it to be that, but it's not that. That's fine. That doesn't really change anything in terms of like the calculus. You could complete the square on the expression and kind of understand like what's going on from that perspective, but we'll just do the calculus, all right? So what's the first order of business? We need to find critical numbers. So how do you do that? A critical number is where the derivative is 0, right? So we have to differentiate this. So what's df dx equal to? Well, it's equal to e to the 9 plus 6x minus x squared times the derivative of 9 plus 6x minus x squared. So that, don't let this exponential notation confound you. That's just another notation for e to the something, yeah.
I think he was right. I don't think you take out the negative in 6. What do you factor that negative 1? Because what would be x squared minus 6x minus 9? And then you can do x minus 3.
Well, the thing is, when I FOIL out like a quadratic, if it's a square, the coefficient of of x squared and the constant will both be like positive or both be negative. Like the sign of the x squared and the constant term have to be shared if it's a perfect square. So I had a mistake. I'm pretty sure. I mean, if you want, I can. Okay. So what goes on here? We have, e to the 9 plus 6x minus x squared times, what's the derivative of this? Well, 6, right? Minus 2x. So if we set this equal to 0, that's for critical points, right? Or for critical numbers. Every critical number corresponds to a critical point here because the domain of the function is all reals. There's no vertical asymptotes. There's no places where the derivative doesn't exist. Every critical number will give us a critical point. That is a point on the graph where the function's defined and we have either the derivative doesn't exist or it's 0. Here it's going to be 0. So this here gives us what, So we've got what? 6 minus 2x equals to 0. 6 equals to 2x if you like x equals to 3. That's my sole critical number for this. All right? So I make my number line for df dx. It's rather boring. There's got a single lonely 3 here, right? And what happens if you plug in 0 into the derivative? We get e to the something, which is positive. 6 minus 0, which is positive. So we get positive. So it's positive over here. So it's positives over here, and it's negative over there. All right? So what can you guys tell me about 3? F of 3 is a what? Local min, local max. What do you think? It's both. You can all have your truth, right? No, it doesn't work that way, does it? So no, yeah, it is a local going up, then going down. It's local max. F of 3 is the local max. By first derivative test. That's what you guys just used. We used the first derivative test. All right, so then what? F increasing on minus infinity to 3. F is decreasing on 3 to infinity. That's where the derivative is positive. That's where the derivative is negative. That's where it's increasing. That's where it's decreasing. All right? Next up, concavity. So we have to differentiate again. Like the concave up, concave down is given to us by the second derivative. So what is f prime prime? So we have to differentiate with respect to x e to the 9 plus 6x minus x squared times 6 minus 2x, right? So that requires product rule. So we get, on the one hand, 6 minus 2x quantity squared times e to the 9 plus 6x minus x squared. And then we get minus 2 times e to the 9 plus 6x minus x squared. Let me walk you through what I just did there. What I'm saying is that when we differentiate the first term, we're differentiating the exponential. We've been down this path before. We did it in the previous part, right? We differentiate the exponential. It brings out the derivative of the argument of the exponential, which is 6 minus 2x. Now I have two of them, so I have 6 minus 2x squared. That's the first term, f prime g. And then the next term is fg prime, which I just get from the exponential times the derivative of the function multiplying the exponential. But what's the derivative of 6 minus 2x? It's just minus 2, right? So that's why I've got this minus 2 here, because the derivative of this is just minus 2. Now, don't stop there, because you're next going to look for places where this is 0, right? So it's imperative that you simplify this. And so I'm going to do it up here so you guys can see it. F prime prime of x is e to the 9 plus 6x minus x squared times. So we got ourselves a 6 minus 2x quantity squared minus 2. There's a smart way and there's a not smart way to factor this. All right? The not smart way is to FOIL it out and then factor. The smarter way is to recognize that you've got the difference of squares. Right? That's what we have. This is the difference of squares. This is a squared minus b squared, where b is the square root of 2. So I can factor that as 6 minus 2, 6 minus 2x plus the square root of 2 times 6 minus 2x minus the square root of 2. That's a plus b times a minus b. And then when is that going to give me 0? Fine, let me factor something out here. I'm going to factor a 2 out of each one of those. So I get 4 e to the 9 plus 6x minus x squared. And that's going to give me a 3 minus x. Why did I factor the 2 out? Dude. See, if I factor the 2 out, what do I have to do to the root 2? I got to divide by 2, right? Oh, anyway, however you want to do this, we're basically solving, 3 minus x plus or minus root 2 over 2 equals to 0, which gives me x is 3 plus or minus root 2 over 2. So these are my possible points of inflection. For them to be real points of inflection, we need to verify that the concavity changes at those points, right? So That's like 1 over root, this is, by the way, root 2 over 2 is also known as 1 over root 2. I mean, however you want to look at it. This is about 0.707. So our possible points of inflection are basically 3 plus or minus 0.7. So you're like, you got like, approximately 2.3, and then over here approximately 3.7-ish, right? And yeah. So what happens if I look at this formula here, and I, for example, plug in 0, what do I get? 0 gives me 36 minus 2, which is 34. It's positive, right? 0's over here. And then these are both linear factors, so we have 2 sign flips. So we have plus to minus, minus to plus. So indeed, not only were those potential points of inflection, they're actually inflection points. So we've got concave up on minus infinity to 3 minus 1 over root 2, and 3 plus 1 over root 2 to infinity. And it's concave down on 3 minus 1 over root 2 to 3 plus 1 over root 2. Oh, so what do you guys think? Oh, we already talked about that. The critical point was a local max. We figured that out already. Notice that you could also use the second derivative test to verify that, right? What's the second derivative test say? The second derivative test says that you look at f prime prime, like we can double check our work a little bit here, right? Notice that 3 is like here, right? Notice that f prime prime of 3 is less than 0, and f prime of 3 is equal to 0. So that says that f of 3 is local max by second derivative test. Now, of course, we don't need another argument because we already have a perfectly good one, but it is comforting to notice that the second derivative test comports with like what we already know, which is that f of 3 is a local max. If you didn't find agreement there, something else we did would be wrong, right? So now we can graph. And the graph, basically, here's 3. And it's got points of inflection like plus or minus here, and it's kind of symmetric about that, I believe. So it's got to look something like this. If I did that right, it should look something like this. Going back to my initial like algebraic comment, so we have y equals e to the 9 plus 6x minus x squared. All right, so if I look at that, that's really e to the minus parentheses x squared minus 6x minus 9. All right. If I complete the square on this inside the exponential, I have e to the minus parentheses x minus 3 squared, and then I have to subtract a 9, so I actually have minus 18 here. Whoa! Yowzers! Whoa, dude. E to the 18 times e to the minus x minus 3. So what I'm about to tell you is like, you try to like get out your handy dandy graphing calculator and just graph this. It's not going to go well for you. Like you should understand the scale of this graph. This right here is 3 comma e to the 18. That's big. So I don't know what your graphing calculator would do with this, but it might not be particularly clear. But the calculus isn't too bad. Anyways, that makes sense. I mean, so just to reiterate, the steps should start to be like clarifying, because we've done this a couple times now. To find increase and decrease, we find critical points, right? Places where the derivative is 0. Draw a sign chart. Where the derivative is positive, it's increasing. Where the derivative is negative, it's decreasing. Then we differentiate again. That gives us where that's 0, where the second derivative is 0. Those are possible points of inflection. Where the second derivative is positive, it's concave up. Where the second derivative is negative, it's concave down. Places where it changes from concave up to concave down are called points of inflection. So like these two guys are inflection points. Example 3. Suppose we had f of x equals to like x cubed plus 3x squared. Let's just do something really simple. Where's that increasing? Where's that decreasing? Where's it concave up? Where's it concave down? What's its critical numbers? And in addition, find the maximum or minimum on, let's say, 1 to 2. So, all right, so let's get to it. F prime of x is what? All right, so we can factor 3x out. We've got x plus 2, right? So x equals to 0 and x equals to minus 2 are my critical numbers. So you got plus, minus, plus, right? So you tell me f of 0 is local what? F of 2 is 8 plus 3 times 4, which is 20. Is the local what? Yeah. Oh man, this is what I was warning you guys about. It could be much worse. Could be much worse. It's okay. What's worse is if you have like 4 of them and you've flipped them in such a way that you can't just erase the 2 numbers. Anyway. Thank you. You do need to put them in order. That does matter a lot. Thank you. So what do you guys think? Local min, local max? What we got?
-2 would be a local max.
Very good. And the other one's min, right? Because we're going negative and then positive. Local max. Local min, rather. How about f prime prime? Well, we've got 6x plus 6. Oh man, I really like this example. It's got all nice, everything's nice in it. Like the possible point of inflection is at -1. So here's my, by the way, I should have labeled this. It's important to label your number lines because we've got multiple number lines in this analysis, right? So you need to know which one's which. So let's see here. Negative over here, positive over here. So yes, we have a point of inflection at -1. And then the last question I asked before I give you guys the quiz was like, come on. The other thing we talked about besides this last time, right, was like the closed set test, remember? Remember the closed set test? So let's see, like, you know, find min max for f of x. We'll do the same one, x cubed plus 3x squared on, let's say, the closed interval from -1 to 2. So what do we have to do? Number 1, f is continuous on -1 to 2. Check. right? It has to be a continuous function. If it's a continuous function, then the closed set test says it attains a minimum and a maximum value on that closed interval. And it also tells you it has to happen either at the endpoints or at a critical point in the middle. So step number 2 is basically we just need to calculate f of minus 1, f of, is there any critical point between minus 1 and 2 for this function? We just looked at it over here, right? Yeah, so 0. So we're looking at, basically minus 1 and 2, right? That's the context. So yeah, we need to check 0. And we also need to check the endpoint of 2. And what do we get? So you just evaluate and you pick winners and losers. Make sure you evaluate the function. We've got minus 1 plus 3 times minus 1 squared, also known as 2. F of 0 is 0. F of 2 is 8 plus... Oh, I shouldn't have said... This was, by the way, this was f of 2, wasn't it? So we already worked that out by accident. Hooray for mistakes. F of minus 2 is actually minus 8 plus 12, which is 4. Sorry about that. Anyway, so yeah, 8 plus 12, which is 20, right? So we have what? By the closed set test, we have that this is the minimum of f on minus 1 to 2, and that right here is the maximum of f on minus 1 to 2 by the extreme value theorem, also known as the closed set test, which again simply says that if you're dealing with a continuous function on a closed set, you can decide maximum and minimum simply by finding the critical numbers and comparing the value of the function there to the value of the function at the endpoints. So now the quiz I have for you guys today, it's got 3 problems on it. Just do your best. If you don't get it all, it's okay. Just try your best and see where it goes.